The final step in prog3.s, before setting an exit code and returning at the bottom, is to store the result in R3 back into val_a. R3 from the prior segment has the entire outcome of this expression, and so we're going to put that into val_a. Now, lines 39 and 40 down at the bottom accomplish this. But how they do it deserves careful discussion and introduces a couple of important new ideas. Now, a first reasonable question would be, why not just use the same arrangement as on line 15 and just write store R3 val_a? That worked well enough for the LDR up here, where we did things like load R0 val_b. Why not just use the same arrangement? And you recall that it operated by offsetting from the PC automatically. So given that val_a is just a few lines down from the instruction in question, why wouldn't PC offset work? Because in fact, val_a is millions of addresses away from the instruction on line 40. It's time to talk about the assembly directives .text, and .data down below, here on line 46. These directives declare memory segments. The working memory of a program is divided into different areas, or segments. Typically, one area of memory is devoted to code and to constant data values that belong with that code. That's the text segment. Line 1 announces that the data and code that follow should go in the text segment. But a different area of memory, the data segment, is reserved for changeable data, like val_a. The .data assembly directive on line 46 declares that the val_a variable is in the data segment. Thus, val_a is nowhere near the code at the end of the program, and PC relative addressing won't work for the store. Why didn't we just put val_a in the text segment? Because the text segment is also marked read-only. Every modern computer has hardware called a memory management unit, or MMU, and this allows the operating system to mark some areas of memory as read-only. It does a lot of other things too, by the way, which we'll get to in later segments. It makes sense to mark the text segment read-only because code should not be modified while running, and any data that is constant should also go in the text segment. It's easier to load it there via PC relative LDR instructions, and you don't want any instruction to change the constant data, even accidentally. Note that val_a and note that val_b and numster_loc are all treated as constant values. The code never modified them. Let's try an experiment here. Let's modify some of the text. I've got a copy of prog3.s here. I'm going to edit that. Let's say I modify it so that the LdrR1 instruction down here is changed to an str. So I'm trying to modify numster_loc. I'll save that. Sorry. Escape and save. Assemble it. Load that. Not quite. There. And then run it. And what I will get is a segmentation fault. This is what happens anytime we do something the MMU doesn't like, including modifying read-only memory segments. I'm going to quickly change that back now. So we've got a good program again. Okay, so since we can't reach val_a via PC relative address, the only choice is to put the address of val_a into a register and then use that register as an address register in a store. And line 39 does exactly that. It puts the address val_a into R2. The equal before val_a says to load the address that the label stands for, not the data at that address. Think of the equal as saying literally the label. In C terms, it's like putting an ampersand before a variable name to get the address of the variable. But wait a second here. Line 39 is strange on at least two counts. First, it's not loading anything from memory, despite being an LDR instruction. It's effectively copying a constant into R2. And second, the value in question is 32 bits long, which once again cannot fit into a machine instruction. We saw the same thing when we were loading R1 with the address of LdrStr on line 20 here. The only way to make it work was to put the value of the LdrStr label into a memory location and then load from that memory location. But now we can just load an address? In fact, the approach used on line 20 is the only one that works. You have to make a memory location with the desired address in it, and then load from that location to get the address into the register. So line 39 is yet another pseudo instruction. When it sees equal val_a, the assembler automatically creates a memory location containing val_a's location, just like the one we explicitly declared as LdrStr in the lines above. It then rewrites the LDR instruction to load the address from that location, just like our line 20 does. So line 39 actually translates into something like this. A load from val_a loc, and then an additional label here with the word that contains the address value of val_a. So that's a pretty sophisticated rewrite. To be clear, it 1. Creates a memory location with the desired address in it in the text segment near the current instruction. And then it translates the instruction into an LDR from the created location to get the desired address. And as already discussed earlier, that revised LDR is really a PC relative load. So go over this carefully to be sure you understand it. It's the most complicated pseudo instruction we'll use in the class, but it comes up anytime we want to load an address. So a few questions. All that extra work with the LdrStr loc earlier, going back up there, wasn't needed apparently. Simplify that earlier code by revising line 20 and dropping 2 other lines. And the answer, in keeping with what we've been saying, is that we could rewrite this as simply equal LdrStr and get rid of these 2 lines here entirely. Now, second question, would that change make the machine language translation shorter? Would there be fewer data words in the translation? Why or why not? The answer, no, it wouldn't be shorter. The use of equal LdrStr would cause the equivalent of LdrStr loc to be created automatically anyway. We just wouldn't have to write it out ourselves. Question 3. When a location containing the address of val_a is automatically created, down here where we wrote that stuff in, to support the pseudo instruction load R2 equal val_a, this is the way it was originally, recall. When we create that location automatically, would the assembler put it in the text segment or the data segment? Why? There are 2 good reasons. The answer there, it has to go in the data segment. It has to be loaded via PC relative addressing, so it must be near the code. And it also should be read-only, since it always contains the same address. Question 4. Does the loaded address, for instance val_a, also need to be near the correct instruction for all this to work? Why or why not? There the answer is no, it can be anywhere in memory. In fact, as we agreed, it's way down in the data segment. The only memory being loaded from by the LDR instruction is the automatically created valet loc word. Okay, so now that we have the address of valet in R2, the rest is easy. Line 40 stores the result we've computed using R2 as the address register. And then the final 3 instructions return that value as the exit code. So I'm going to go over and run the program, and we'll find that the exit code is 103. Confirm. Got my modified program back where it should be. We'll load it, run it, and that proves that our computations were correct.